Right, we're live. No, yeah, we're live. Excellent. Okay, so this stuff is a little bigger deal. We're going to focus on looking at three-dimensional shapes now. We've looked at two-dimensional shapes. We just got done looking at polygons, right? Now we're going to look at polyhedra, so three-dimensional and other stuff too. Three-dimensional things, and specifically we're going to look at focusing on things like lots of stuff, but primarily volumes and surface areas. This is important because it's stuff that you use a lot more than some of this other stuff in geometry. It's all important, but this is more important. This is stuff that you would consider a lot in architecture, graphic design, chemistry, when you want to model what molecules look like. We use polyhedra for that. So this is a pretty big deal. I'm going to skip. I've got a little PowerPoint that goes with section 1.7. That's the one section we do from chapter 1. It has to do with perimeters and areas. The only thing that would be remotely new to you about any of that would be, and it's not really new, we just haven't talked about it this year, would be circles. Looking at calculating circumference and areas of circles, and that's no big deal, just a formula you use. If there's time at the end, I seriously doubt there will be, I'll pull that up. But otherwise, you guys just click through that little PowerPoint maybe on Monday when you go to the lab, or sooner if you want to. But take a quick look at that, 5 minutes, all it'll take. This is a little bigger deal. I want to focus my attention on this, exploring solids. So, without further ado, here's the first animal we're going to look at. It's called a polyhedron. Okay, a polyhedron is a solid that is bounded by polygons. So it's as though we took a big block of dough and we're going to cut this thing in such a way that we're creating faces. So the flat faces, the flat surfaces we call faces, that are polygons. Okay? So that's just an example of what a polyhedron might look like. Okay, this is a face, right? As I said, those are the flat surfaces. Now you know it's a polyhedron if the faces are truly flat. So in other words, if I were to hold this shape in my hand so that one of the faces is flat and horizontal, I ought to be able to put a marble down any place on that face and have it not move. Now if the surface weren't flat, let's say it were a little bit crowned, then the marble would roll off, right? So that would disqualify it. That wouldn't be a polyhedron. If it were cupped a little bit, the marble would always roll down to the bottom of the cup, right? So that would disqualify it. But if it's really polygonal, polygon faces, then that marble's going to sit still until I tilt it a little bit, and then it'll roll around, right? What does that imply about the other stuff? Well, we know that the places where the faces meet are called edges, and the edges are always going to appear as line segments. They have to, if this is a polyhedron, those edges are straight. They're line segments. They're not curvy. If they're curved, we know we're dealing with something different. And then the places where the edges meet are called vertices. So there's an example of a vertex. Okay? Makes sense? So that's the anatomy of a polyhedron. Okay, so just there. Okay, and then the plural for polyhedron is polyhedra. Okay? All right, so take a look at these then. Take a second and just think about this. A, B, and C of those examples, which are polyhedra and which are not. How about A? Does that work? Yeah. Is that a polyhedron? Yeah, that works. Sure. How about B? No. No good. No, look at this. This edge is curved, so that face is not flat, right? So that doesn't work. How about C? Yes. Yes. Yeah, that would be a polyhedron. So the drawing's a little warped, but assuming that those are supposed to be all straight lines, yeah, that's a polyhedron. Okay, so polyhedrons, that's one of the things we're going to look at. Now, polyhedrons are, here, let me have, real quick too, I forgot to mention this. Polyhedrons can be random. And we're going to look at a lot of cases where they're just, they don't look like anything special, but they can be special too. They can be prisms or pyramids. Now, what does it mean to be a prism or a pyramid? A prism means that there are going to be two faces that are parallel, meaning if I stick this thing on a glass coffee table, say I set it on this bottom base, we're going to call that, on the bottom base of this prism, which is triangular, then the top base is going to be parallel to the bottom one, meaning it will also be flat. So if the coffee table is flat, I could place a marble on top of this thing and it wouldn't move. It's going to be horizontal, right? The other thing that has to be true is that all of the edges along the sides, we'll call these the lateral faces and the lateral edges. So when I set it on a coffee table on one of the bases, all of the sides of this thing, the lateral faces and the lateral edges, are going to have certain characteristics. All of the lateral edges are going to be parallel. One thing. Okay. So in other words, that triangle on the top can't be smaller than the triangle on the bottom. They're congruent. Okay. All right. So there's a prism, and we'll talk about those a lot more in later sections in the chapter. But that's your first introduction. A pyramid is a little different. Pyramid is something where if I set it on the table, so it's got a base that sits on the table, then all the faces are going to come to a point above the table. Now, it could look different. This one looks like a nice symmetric pyramid, but I could even stretch it out over this way and warp it so the top is not, the apex is not lined up over the center of the base. Now, we could do weird stuff with this and still have it be a pyramid, but typically that's what we think of with a pyramid, right? What else? Okay, stuff other than polyhedra. We can look at other kinds of solids too. Cones and cylinders, for example. Cylinder, think of a cylinder like this. Think of a cylinder as starting off with a prism and just kind of cutting off the corners to make the lateral faces of this thing, the sides of it, rounded instead of polygons, right? So we end up with something like this. You can see how they're sort of similar. This is jagged, this is smooth, but they both have faces that we could call bases that sit on the coffee table and are parallel. Wouldn't you agree with this cylinder? If I sit this thing on a flat coffee table and I put a marble on top right there, it's not going to move, right? So that's a cylinder. Definitely not a polyhedron, right? This is clearly, curvy. That's what it looks like, though. It's circular bases, a tube-shaped side, the lateral surface of this thing, the side surface is a tube, but similar to a prism. Now, pyramid is like a cone. If we take a pyramid and just round it out, it ends up looking like a cone. This time, the base that sits on the coffee table, instead of being a square or a pentagon or a triangle like we could have with a pyramid, it's a circle. Okay? And then up on top is the point of this, the point of the cone. I could distort it. I could drag that point over to the side a little bit and skew this thing. It'd still be a cone. It just would be sort of a weird-looking cone. And then last of all would be a sphere, and that's pretty simple. Just a solid ball would be a sphere. Okay, so moving on with this. We can classify polyhedrons in some other ways. We can talk about a regular polyhedron, for example. Now, we've talked about regular quite a bit this year. If two polygons are regular, like say a regular hexagon, what does that mean if I say it's a regular hexagon?
All angles and sides are congruent.
Good. All the angles and sides are congruent. Very good. Okay, and that has a real characteristic, nice look to it, doesn't it? Everything it has lots of rotational symmetry. Okay, so same kind of thing happens with polyhedra. We can have weird-looking ones, and we can have very symmetric, regular, nice-looking ones. A regular polyhedron is one where all of the faces are congruent, regular polygons. So there's an example of a regular polyhedron. In this case, what are the faces? Yeah, what kind of triangles? Equiangular also, it'd be regular because they're equilateral and equiangular, right? And we just call that an equilateral triangle usually. But notice that all the sides are congruent. We didn't draw it in, but we also know, of course, that all of the angles are congruent on each face. Right? Oops. That's all. That's all. Okay, convex versus concave. Now, we talked about this too. We said with polygons that normal polygons, sort of, the kind we typically visualize, are convex. But we could have concave polygons also, right? Concave polygons have divots in the edges, right? Where same thing could be true with polyhedra. We could have regular convex kind, and then we could have non-convex. Convex just means that if I pick any 2 points on the surface of the polyhedron, if I connect those 2 points, the segment that I create that connects those 2 points will always either be inside the polyhedron or on one of its surfaces. It'll never actually leave the polyhedron. Okay? If it's concave, that's not the case. Here's an example. There's an example of a concave or a non-convex polyhedron. Notice that if I pick points like there and there, or any place along that edge, for example, when I connect those 2 points, the segment that connects them, or the line that connects them, however you want to think of it, travels outside the polyhedron, outside the shape, right? So that's an example of concave or non-convex. Is that regular? Not even close. Right, look at these weird shapes. Look at that face right there. That's obviously not regular, is it? Okay? What about this? Is it convex? Is it regular? This octahedron. It's regular, isn't it? Yeah, it's regular. All of the faces appear to be equilateral triangles. Is it convex or concave? Convex, for sure, yeah. Okay, convex and regular. What about this guy? That's also an octahedron. Same number of faces. Convex. Good. Is it regular? No, definitely not. Okay, so whoops, convex and not regular though. What about this one? That's also an octahedron. 8 faces. Concave. Sure. It looks like if I connect points there and there, for example, or there and there, I'm going to have to move outside the shape, outside the polyhedron. So it's concave, regular? Nah, definitely not. Okay. Okay, cross sections. Now, cross sections are really important in math and in like design. If you're going to do any kind of architecture, or you always want to see a cross section of a house. You want to see what the inside looks like, stuff like that. So cross sections are what we get when we slice through something solid. So imagine that you've got a big spherical wad of dough, and we're going to cut through that. If I cut through it and then hold up the half of that piece, let's say, or the piece that is remaining after we discard one of the 2 pieces, what is that new face going to look like that I've created by the cut? So what is, I cut through this thing and I take the top and throw it away. If I look at the bottom and I hold it up, what kind of cross-sectional shape have I created? Circle, yeah. In fact, that's all I'm going to get, isn't it, for a sphere? There's no way to do anything different. If I cut through a sphere, I'm going to get a circle. Now, I can change the circle. What if I cut through near the top instead of right at the equator? What's that going to do to the circle? It's going to make it smaller, yeah. What if I cut through at an angle, like up here? Still just get a circle, don't I? Right? There's no way to get anything else. But there are some other shapes that we could cut through that would create different kinds of things. Let's look at, for example, a cube. What if I take cross sections of a cube? Now, the obvious one is if I cut right through the middle, what do I get? I get a square. Yeah, here's my challenge to you. I want to take a ton of time on this, but I want you to think about this for a second. See if you can come up with some other possibilities. There are more than you think. More than you think. What's one of them? Cut off the corner. Okay, well, I'll tell you what, let's look at that. I've got a little tool here. I put this on the website, too, so you can play with it. I might even have you come up and do some of this stuff. Now, the way this works, each of those little points on here is a place that I can activate, and I'm going to activate 3 of them, and then 3 points defines a plane. There's only one plane that can cut through 3 points. So the suggestion is, what Dylan's saying is, how about if I cut through, like, maybe right there, and right there, right? And if I create, now look at that. Okay. There's a triangle. In fact, what kind of triangle is that? Yeah, it's equilateral, isn't it? Okay. Now, can somebody create a triangle that is isosceles? It's not equilateral. Who wants to be right here? One. Let's you give this a try. So there's equilateral. Let's try isosceles. So maybe 3 points. Yeah, it's kind of hard to. You just kind of you got to make sure that white one's hitting that. Okay, right there. I'll down a tiny bit. Here, you point to him, and I'll do it. Okay, this one. Okay, so that guy. Yeah. Okay. This one. Okay. And say this. No, this one. Okay. This guy. Okay, so if I create, yeah, good. That looks good, right? Everybody agree that's isosceles? Okay, these sides are same length, longer than that one is. Okay, agreed? Good. How about a scalene triangle? One that's got 3 different length sides. Anybody want to take a shot at that? 3 different lengths. So we got different kinds of cross sections we can do. There's our pentagon. There's our triangle. Okay. Here's something that seems a little surprising, I think, at first. There are, how many regular polygons are there? Polygons, 2-dimensional. Here, infinite, sure, right? They're infinite because I could have a regular 3-gon, that's an equilateral triangle. A regular 4-gon is a square. A regular 5-gon is a regular pentagon. Regular any number of sides, I can make a regular version of that, right? Okay. Not the case with polyhedra. Polyhedra, we are limited. There are 5. Count them 5. That's it. 5 regular polyhedra that we call Platonic solids, and that's just basically that's a relic of Plato. The philosopher Plato thought that these certain shapes were more, they had more power than shapes that weren't nice and regular like this. So these were extremely special because there are only 5 of them. 5 3-dimensional polyhedra that have this property. Remember, regular means that all of the faces are congruent polygons. So this one makes sense, doesn't it? Right? I mean, we can see here pretty easily that all of the faces on this one are regular triangles, equilateral triangles. What's another one you can think of that's pretty simple? A regular polyhedron. So all the faces are congruent. There's one that's pretty obvious if you think about it. Can you think one? Maybe I should roll the dice and pick on somebody. Okay, what would you call that?
Cube.
Cube, yeah, there you go. So if we look at the other 4, that one's pretty simple, right? The cube you can see. The others are getting a little harder. The octahedron, maybe you could get. That's like putting 2 pyramids, on top of each other. So all the faces are once again regular 3-gons, equilateral triangles. But these other 2 are weird. Dodecahedron has 12 faces. Notice that all of the faces are regular pentagons. An icosahedron has 20 faces, and once again, all the regular faces in this case are equilateral triangles. Those triangles pop up a lot. 3 of the 5 have faces that are equilateral triangles. That's it. Try as you might, you cannot find another, there is no 6th. That's it. Now I want to see if you can notice something here. See if you can notice something about these. Look at the numbers of faces, vertices, and edges. Oh, and before we do that, how could we count? The faces and vertices are not that hard to count. They're okay. Number of faces, we can just, we can sort of visualize that. The number of vertices are pretty easy to count, but the number of edges are harder to count, partly because there are always more of them. Okay, those are a little harder to count. Can we come up with a trick for calculating the number of edges, for counting the number of edges. Let's take this guy as an example here at first. We've got 6 faces, right? All of them are squares. Now, each of those faces, those square faces, is going to connect to how many edges? 4, right? Each of the sides connects to an edge. Get an idea?
The sum of the faces and the vertices are two.
Oh, okay, now there's something good. That's the big pattern. You saw that. That's good. If we're just trying to count the edges, if there are 6 faces, each face connects to 4 edges. 6 times 4 is 24. And yet there are only 12 edges. How did I miscalculate? This one's got 6 or 4 edges. This one's got 4 edges. That one, there's 6 of them. What did I do?
Because they all, each edge is shared.
Oh, I double counted. Sure, because each edge is shared by 2 faces. By definition, right? Isn't an edge, by definition, where the 2 faces meet? That's the joint where they meet. So we always know that each edge is always shared by 2 faces. So if we just multiply the number of faces times the number of sides on each face, we're always going to get twice as many as edges as we truly have. So divide that number by 2. The number of faces times the number of sides per face divided by 2 will always give us the number of edges. 6 times 4 is 24 divided by 2. Let's see. 8 times 3 is 24, divided by 2 is 12. Okay, good. And Evan saw the other big relationship here called, this is Euler's relationship, or Euler's theorem. Notice that if you add up the number of faces and vertices, it's always 2 more than the number of edges, regardless. It doesn't even have to be a regular polyhedron. That works for any polyhedron. So 12 plus 20 is 32. Oh, that's 30 plus 2, right? 8 and 6 is 14, 12 plus 2. 20 and 12, 30 plus 2, right? Make sense? And it works for something like that. Whoops. There's the relationship. F stands for the number of faces, V for the number of vertices, E for the number of edges. On any polyhedron, F plus V has to equal E plus 2. What about this guy? Okay, this has 14 faces. Okay. Each face, it looks like, is either going to be a regular hexagon or an equilateral triangle. So there are 8 triangles and 6 octahedrons, right? The triangles, if we want to figure out how many vertices there are, we can do that. How many edges, how many sides are there on each of these triangles? No. Each of the triangles has how many sides? 3. Each of the octahedrons has how many? I think I said the wrong card. 8. So I'm going to get a total of 8 times 3 plus 6 times 8, right? That's the total number of edges that are shared. So that's going to give me, what, 24 plus 48 is 72? Did I do that right? 24 plus, yeah, 72. So if there are 72 shared edges, how many are there total? 36, right? So we know then, let me write this down. So we know that we've got 14 faces. We have, what did we say, 36 edges?
No, 17.
Divided by 2,
Oh, yeah.
right? So how many vertices would we have? Well, what's our relationship? What's Euler's theorem? They're always the most edges. So what plus, how'd that work?
Faces plus edges.
Okay, F plus V
Oh,
equals E plus 2. Now, what do we know already? Well, we know F and E, so I can solve for V, right? If I plug 14 in for F, plus V equals 36 minus 2, well, we can do that. 36 minus 2 is 34. Minus 14, 20, right? So then V is 20. How about that? Yes?
Wouldn't it be plus 2?
Oh, I'm sorry, plus 2. My mistake. You got me. You're right. Plus 2. So 36 plus 2 is 38. Sorry. 38 minus 14, 24. Good. Okay. So V is 24.
Yeah.
Okay. There's what we just did, right? There's Euler's theorem. Plug in the stuff. And we got it. 24 vertices. Okay? So now here's where the chemistry comes in. In chemistry, especially when we're dealing with crystals. Now, I'll bring in a good picture. I don't have it with me right now. But you can see that if you take a crystal, like say if you had a big block of salt, for example, and you crack that block of salt, what you'll notice is that it's going to break along nice flat surfaces. Or if you take a piece of quartz or something like that and you break it, it cleaves, it breaks on these flat faces. And so a really good way for us to model the behavior of crystals is with these polyhedra. The molecule that makes up the substance, in this case we're looking at table salt, sodium chloride, is going to determine the shape of that molecule determines how they all fit together, and so how this thing is going to break, even on a big scale where there are billions or trillions of these molecules glommed together to make this big piece of salt, they're all going to end up fitting together in ways that are based on the shape of that molecule. We know that for sodium chloride, the structure, and we can see this if you look under an electron microscope, you can even see this. It behaves like a regular octahedron. Okay, so that's the one. If we go back a little bit, here's what this isn't a very good picture. It's hard to see there, but if we go back, here's our regular octahedron right there. So that's what each molecule fits together like. Okay, so we could go further with this, and I know we're getting pretty close to the end here. So if we wanted to know, for example, the number of molecules that share edges, we want to know how they pack together, doing a little chemistry. We could do that because we know the shape. We know that an octahedron has 8 faces and 6 vertices, so we can just use that little formula we've got, and we can find the number of edges. What's it going to be? F plus V equals E plus 2, right? So 8 and 6 is 14. That must equal E plus 2. That's 2 more than the number of edges. How many edges are there? 12, sure. Right, here's the math. Right, we know that. We can plug in the values. So I get 14 on the left side. Subtract 2 from both sides, and I find out, sure enough, that there are 12 edges. And so that's important for us. We need to know how these molecules connect to each other when we're studying table salt for whatever reason. Okay? So there it is. Soccer ball. Soccer ball, even though, is it truly a polyhedron? No, it's not, because these aren't flat, are they? It's a ball, and so they kind of puff out. But it can be modeled by that. This is very much like a polyhedron. If I were to take a soccer ball and just flatten those out, that soccer ball would be a polyhedron, wouldn't it? Okay? So we know here that it resembles a polyhedron with 32 faces, 20 are regular hexagons, 12 are regular pentagons. So all the white ones on here are hexagons, the black ones are pentagons, right? How many vertices does that have? That'd be hard to count. It'd be really hard to count. You have to draw on your soccer ball, or you wouldn't be able to do it. So how could we do that? What do you think? We know the number of faces. We could count those. 20 white, 12 black. How could we do that? If we knew the number of faces, could we calculate the number of edges?
Yeah.
How do we find the edges? Can we do that?
Are there 60 verses?
There are. That's what we'll see here in a second. Yeah. So we have 20. We said we have 20 hexagons, right? So 6 times 20 is going to give us 120 shared edges from that. We had 12 pentagons. 5 times 12 is 60. So 60 shared edges from those guys. So a total of 120 plus 60 is 180. I have 180 shared edges, but because they're shared, we got to cut it in half. Right? So we end up with a lot. We end up with 90 edges on this thing. Right? So if there are 90 edges, and we already said 32 faces, how many vertices would there be? Well, we know, here's our formula, right? So we can apply Euler's theorem. And so we knew faces was, what did we say, 32? Edges was 90. That's easy. 90 and 2 is 92. Subtract 30, what do we get? 60. There you go. Very good. 60 vertices. Okay? All right. Wow, we made it. I'm amazed. That was good. So this is, I'll put all this stuff up there. If you want to take a look at this again, you're welcome to. But you guys will be kind of on your own Monday and Tuesday, and then we'll come back together and talk about things. All right.